and welcome back. We are talking about section 5.5, additional applications of integration to business and economics. So we have tackled the first objective. We've kind of broken this second one down into some pieces, but we did consumer willingness to spend. We talked about consumer surplus. And this last one, we're going to talk about producer surplus. And then one other topic that's not actually part of this section, but we need to address it because we're not going to do the full section on this. I'm being very obscure, but we'll talk about it when we get there. Okay, so let me get to the right slide and we will begin. So we talked about consumer surplus, which is the demand side of things. So now we're going to try to talk about producer surplus. So consumer surplus, so the one from the previous video, basically said something like, whenever you have sales that take place at a price lower than the consumer was expecting, then they view that as a good thing because they were willing to pay, say, $500 for something, but they only had to pay $380. This is viewed as a savings of some sort or a surplus in this terminology. So now we're looking at the supply side of that. So we have our nice little generic supply curve here. And so this represents the prices at which the producers, those who are making the product or selling the product, are willing to make this product. And then P naught is the market price. So if you imagine you're a producer and you're willing to sell your product for, $300, and instead you're able to charge $350 for that, because there's a price discrepancy between what you're willing to sell at and this market price, that's going to feel pretty good to you because that's money, extra money that you weren't expecting to be getting. So this whole area was viewed as producer side surplus. And it has a formula that's very similar to consumer surplus. We've got our, basically this rectangle is the sales that are actually taking place. So this whole area down below P naught, basically. So that rectangle has area P naught times Q naught. But these prices below the supply curve aren't actually valid prices from the producer's perspective. They're too low, so they don't want to sell down here. So so what we're going to do is basically subtract off that area. So there's us subtracting off the stuff underneath the supply curve. And that's what this integral represents exactly, is the area that's underneath this supply curve. So what's left over is the blue shaded region up top, which is exactly the difference between these two areas. So let's try an example. So we'll borrow our same functions from example 2. So here's our demand and supply curves. We're still going to work at market equilibrium, and then we're going to try to investigate the producer surplus of this. So just so we don't reinvent the wheel here, we're going to borrow some of our values from the previous exercise. In particular, here was our Q naught, and $20 was our market equilibrium there. And so our producer surplus is going to start with the formula we were just handed, and then we're going to plug in some of these values. So no big surprises there. And then here's the excitement, the new stuff that's going on. So our supply curve is this expression inside of here. I'm going to try to write this so it doesn't interrupt the other stuff. And then here's our Q naught again. So these 1200s are the same for a good reason. So we're basically looking at the area under the supply curve, so we can subtract that off because that's not actual valid sales. So then we've got our product, 20 times 1200 gives us this 24 grand. And then this integral is just some power rule. Our Q is going to go up to Q squared and divide by 2, so it's going to make more decimals for us, but all right, such is life. This 8 is going to go up to a Q to the first, and then we're going to evaluate between 1200 and 0. Okay, so we're going to do our fancy fundamental theorem of calculus business. We're going to get a value. I guess you might notice all of this is 0. It's just a bunch of zeros together. All of this here ends up being $16,800, and for a grand total of $7,200. And just to remind ourselves about the interpretation of this, producer surplus is sort of, again, a psychological kind of device, but it's saying that, look, I thought that I was only going to be able to make about $16,800 from selling this product. But because the market price was priced up higher than the supply curve, I ended up making about $24,000, which is fantastic. So that means that the difference between my expectation and actual sales was $7,200. which is delightful. So that's more money in my pocket than I had anticipated. So there's producer surplus, very similar computation to consumer surplus. If you're not in my class, that is Mike Price's class, then you can probably stop here. But we're going to continue on to one other topic. And basically, this is just a special integral, an antiderivative. You notice that this is a indefinite integral, that we're not doing the definite piece of this. But this is an integral that we would not be able to compute otherwise. And the main complication is that there are variables, so here's an x, times something else that has x's in it. So far, we don't have any rules for how to tackle such a thing. So this is a very specific antiderivative family. And the reason we're doing this is because, especially in this section, we come up with a number of interesting examples where if we did future value or present value where the continuous income stream changes at all, so it's not just a constant, then we would be kind of out of luck without something of this form. The more general process that you'd go through to find this antiderivative is called integration by parts. That's section 6.1 in the book. We're just not going to tackle that because it's a more complete process than we actually care about for our purposes. So we're going to, because we still have at least this one type of integral that we need to know how to compute, we're going to basically say, here's the special antiderivative that we might want. So it's the antiderivative of something like this looks like that constant, 1 over k, e to the kt, or kx, and then all of that times x minus 1 over k. So we're going to see the comparison between this and an integral that we have known how to compute for a while. And we're going to do that within the context of another present value problem. So we're going to consider a 10-year investment. We're going to be depositing $20,000 per year initially, so that's the starting piece. I mean, before I start underlining other stuff, we can at least note, all right, we've got a 2% per year rate of return. So there's our R. However, here's the catch. Those deposits, instead of staying constant at $20,000 per year, they're going to go up to $22,000 at the end of that first year, and then $24,000 for year 2, $26,000, $28,000. So they're actually accelerating a little bit as we go. So in other words, if we were looking at a graph of f of t, it would actually have some kind of positive slope instead of being a constant. Again, one of the hardest things to remember about this is that the f of t in our present value computation already is a rate. It's an income stream. It's a rate at which money is being put into an account. So it being constant means you are depositing at a constant rate. It doesn't mean that more money isn't going in. It means you're not changing the rate at which that money goes in. So if we start at 20 grand initially, and then we go up by 2,000 per year, that's going to look a lot like a line with a slope of 2,000 and a y-intercept of 20,000. So when we go to do our present value, we're going to look at our present value formula. We're going to have f of t be that linear function we just came up with, and we're going to start dumping stuff in. So here's where we hit trouble. This is not really an integral that we are particularly good at managing. I think we can make it work, but right now we've got two things getting added together, and they're all times something else with variables in it. So one good strategy to start things off would just be to distribute. Just break these two things out into their own integrals and then try to manage them from there. So this guy right here is fairly familiar to us. It's a constant times e to the kt. So we have a great formula for that. That's just our good old-fashioned 1 over k e to the kt. This guy over here, you'll notice it seems like such a small difference, but it really is enough. You have a variable times e to the something else with variables in it. And if you think back to derivatives, we needed a special rule for derivatives of things that had products of variables. So since we've got variable things getting multiplied here inside of an integral, you'd have to imagine there'd be the same kind of concern. So that's why we have to turn to this fancier antiderivative that kind of bails us out. And it bails us out by giving us a separate formula that is definitely more complicated than the one we started out with for just e to the kt. But the good news is it's good enough to make this work. In both cases, the constant 2,000 can get pulled out in front. It's just a constant multiple. And we can do our evaluation at the limits here. So we get our two antiderivatives. Again, we don't need plus c with a definite integral because they would just get subtracted anyway. So we'd plug in 10, plug in 0, plug in 10. Remember, to two different spots, there's a t here and a t there. Plug in 0 everywhere, and I think we get a grand total of something around 268,000 and some change. So it's important to remember the interpretation here. So this is not just saying that if I do this 20,000 in the first year, 20,000 in 22,000 in the second year, and so on for 10 years, that it will be worth 268,000. That's not what this is saying. It's saying that if instead of doing that annual deposit thing, well, really continuously depositing, if instead you just deposited a lump sum of 268,000 and some change, you would end up with the same value invested as if you did this with the annuity, the thing where you deposit 20,000 in the first year and 22,000, etc. None of the computations we've done so far have said how much would those two accounts be worth. In case you're interested, if you did do the future value, which is what the annuity would be worth at the end, you'd get about $328,417, something like that. No, I did not do that off the top of my head, but I should have just said nothing so you could be impressed with me. What that means is if you took this thing and you did PERT, then you would end up with that same value. If you did 268,000 as your principal and e to the RT, then what you'd end up with is the exact same, I'll get back to it, you'd end up with the exact same value at the end of that as if you did the annuity. So in other words, your PERT model is giving you this lump sum to start with. That would end up with the same as the future value of this annuity where you're accelerating slowly, starting with 20,000 a year. Okay, so last thing, we've got a U-try problem, and it's part of this integration deal. So if you put your video on pause now and give this a try for a couple minutes, then we'll come back and I'll do it with you. Okay, I'm assuming you're coming back now. So the thing to notice here that's sneaky and we'll have to get used to is that we have this extra constant getting multiplied to something, this extra variable getting multiplied to something else that also has variables in it. So you will have to remember that special antiderivative. So I'll put this off to the side here. So if you have t e to the kt, then your antiderivative is going to end up looking like 1 over k, e to the kt, and then t minus 1 over k. And don't forget your constant from integration. This is an indefinite integral, remember, so we're going to end up with a whole family of antiderivatives. This constant shouldn't worry us too much, so we can just pull the 10 out in front. But other than that, we've got t e to the, and in this case, k is 0.01. So we've got our whole expression here that will play out. 0.01 e to the 0.01 t minus 1 over 0.01. And we could certainly tidy this up a little bit. I'm not sure how much it's worth it, but we could get some other slightly simpler answer. For instance, 1 over 0.01 is 100. We could combine these two guys, but we'll stay lazy and just leave it like that. So that's it for 5.5 plus this bonus objective with the special integral. We'll be back with an entirely new chapter in the next video.